Hello students, good evening, welcome everyone. My name is Satish. Today we'll discuss about matrices, very basics of matrices. You might well be aware of all these concepts which we are going to discuss, but to keep you on track, like let us just revise them quickly and then we can discuss on some problems on them. Okay, so most of you know what is a matrix, right? What is a matrix? A matrix is nothing but a rectangular arrangement of data, right? Say A, B, C, D, E, F. So if I say this is an arrangement of data in a rectangular form, now why I'm calling this as rectangle is like it has length and breadth, right? So here this length is divided into parts which are called as columns. So what are the columns here? The number of columns here are 3. And what are the number of rows here? The number of rows are 2. So the order of the matrix, this is the size. See, how do we talk about the size of the matrix? See, this is a matrix and I have say another matrix 1, 2, 3 and 4. This is another matrix. What is the difference between these two matrices? So this is a matrix whose size is slightly bigger than the size, in the sense like, you know, in one aspect, in one orientation. Say this is a 2 by 3 matrix. The order, see, how do we talk about a matrix is by their order. Order is nothing but the number of rows by the number of columns. So here this order is 2 by 2. Say suppose I have a matrix 1, 2, 3. This is a matrix again, and the order of the matrix is 3 on 1, which is like 3 rows and 1 column. So we talk about matrices in terms of their order, which is nothing but the number of rows by number of columns, right? So suppose in a matrix, if we have the number of rows and the number of columns equal, say A, B and C, D. These are the two these are the elements of the matrix where we have 2 rows, 1 and 2, and I have 2 columns, right? I'm sorry, 1 and 2. Now the rows and columns of this matrix are equal. The order of the matrix is 2 by 2. So this type of matrices are called as square matrices. For example, if I have say one more example for a square matrix is say A, B, C, X, Y, Z and P, Q and R. This is one more matrix whose order is 3 by 3. So this is also one more example of a square matrix. So a square matrix is nothing but a matrix whose number of rows and columns are equal. And if the number of rows and columns are not equal, say suppose I have A, B, C, 1, 2, 3. Say this is one more matrix. Here the number of rows are 2 and the number of columns are 3. So this is called as a rectangular matrix. When the rows and columns are not equal, this is called as a rectangular matrix. So it can be in this way also, like 1, 2, 3, 4 and 5, 6. This is one more matrix whose order is 3 on 2. So this is also one more example of a rectangular matrix. So I think you understood like what exactly is a square matrix and what exactly is a rectangular matrix, right? So now let us consider a matrix, say A, B, C, D, E, F and G, H and I. This is a matrix. Now in this, if I talk about the elements one more thing, like the data parts which we put into this matrix are called as the elements. So this is, see, the circled one, A is the first element. We generally name it as say A11. This one is called as A12, A13. See, the 1 specifies the number of the rows in which it is, and the next number specifies about the column. This is the element in the first row. This is the element in the first row and second column. This is the element in the first row and the third column. So can you guess what this will be? This will be A31, and this would be A32, 2. See, I'm using A to generalize, say, okay, let me say X also. You can say X11, X12, X13 to say the element, the location of the element, right? It's not the actual element which we considered here, right? And this one is A33. So these are the elements. We can address each element by the location of them, location of it in the matrix. For example, if I want to talk about this E, I can say this is A22. Right now, if you look at this, A here is the A11 element, and E is A22 element, and I is A33 element. Why are we talking about these elements? If you look at it carefully, these are on, like, you know, in one line, like in one line, they lie on one line, which is called as a diagonal of the matrix. This is called as the principal diagonal of the matrix, and these elements are called as the diagonal elements of the matrix. Right, A11, A22, A22, A33. Suppose I have a matrix of order 4 by 4. Then what will be my diagonal elements? My diagonal elements will be A11, A22, A33, and A44. So the nth order matrix will have so on up to ANN as the elements in the diagonal. Right, so diagonal is nothing but the elements which fall in the equal number of row and column. Like the row number and the column number should be the same, like first row first element, second row second element, third row third element, and so on are called as the diagonal elements. Now let us talk about matrix. Look at this matrix, see what you understand from this. What can you say about this? Like A00, 0A0, and 00A. So what is the speciality of this matrix? Like if you look at this carefully, you have the diagonal elements. All the diagonal elements are non-zero in the first place. Remaining all non-diagonal elements are zeros, right? So the diagonal elements are non-zero, and all of them are equal to one particular number, which is A. It can be 5, 6, 7, whatever it is, one particular number. So this is called as a scalar matrix. When the diagonal element, the principal diagonal, has the same element throughout it, and the remaining all elements are 0, then it is called as a scalar matrix. So what if the elements are, the diagonal elements are non-zero and remaining all elements are 0, but the diagonal elements are not equal, say 0, 0, 0, and here I have 3, then this is called as simply a diagonal matrix. It is not a scalar matrix. This is not scalar, this is scalar. This is just diagonal matrix. So a matrix is a diagonal matrix if the principal diagonal has non-zero elements and the remaining all elements are 0, and they are not equal. The diagonal elements are not equal, they all are different elements, then it is a diagonal matrix. And a scalar matrix is again a diagonal matrix in which all the elements in the diagonal are equal. Here it may equal, may not be equal. This is also a diagonal matrix, right? But it has one more special property, like, which is an added property to it, which is all the elements are equal. So it is called as, it is given a special name called as scalar matrix. Got it? Now let us observe this matrix and tell me what you see here. So many zeros, right? Yeah. So what do you observe from this matrix? Like, see, all the elements are 0 here. Every element is 0, right? So what is this matrix like? Does it have any value? It has a value which is equal to 0 actually. So this is called as 0 matrix. I'll tell you where we'll use this and how it will help us in calculation of some situations. When we go into advanced levels, I'll let you know like how we can use this. So when all the elements of the matrix are equal to 0, like each and every element in the rows and the columns, like all the elements are 0, then we call it as a 0 matrix, right? Now let us see one matrix here. See 2, 3, 4, 5, right? So this is a square matrix, right? This is a square matrix of order 2 by 2. If if we want to find the determinant of this matrix, like what is the determinant of this matrix? It is like if my matrix is A, B, C and D, the determinant of the matrix is given by AD minus BC, the product of the principal diagonal elements when it is a 2 by 2 square matrix, and minus the rest of the two elements like B and C will give us the determinant. So if this is A, we denote this as this way, or we also write it as det A. Now if I want to find the determinant here, AD is 2 times 5 minus 3 times 4 equals to 10 minus 12, which is equal to minus 2 is the determinant of the matrix. So this is how we calculate the determinant. So what if it is a 3 by 3 matrix? Say suppose I have A, B, C, D, E, F, G, H, I. So how do we find out the determinant of this type of matrix? Let us take some simple these ones to understand this more easier, like A1, B1, C1, excuse me, A2, B2, C2, A3, B3, C3 be the elements. Now if I want to find the determinant of this, it is A1. See, I'm talking about this element A1, the first number. Then you completely remove the first row, the row and the column in which the element is existing, right, and take the minor, this is called the minor, the remaining part, which is B2, C2, B3, C3, right, minus B1 times, now you have to remove this and this part, like this is gone, so you have A2, C2, A3, C3, and the minor, each determinant can be calculated from the minor very easily, like B2, C3 minus, let us complete it first. So if I'm talking about C1, then you remove this column and this row, you get A2, B2 and A3, B3. And then so A1 times, so this is B2, C3 minus B3, C2 minus. In the same way you calculate this, B1 times A2, C3 minus A3, C2 plus C1 times A2 B3 minus A3 B2. So this is how we calculate the determinant of a 3 by 3 matrix, even 4 by 4. So you keep on doing this until you know if 4 by 4 is there, you take like one row and one column and you get one more matrix again, and in that you select a column and row, and again you get a minor. You keep doing that. Now, when can we say two matrices are equal? Say suppose I have two matrices, say A is equal to 1, 2, 3 and 4, and I have one more matrix which is equal to B, 1, 2, 3, 4. Can I say A is equal to B? Let me tell you. See, if you are trying to compare two matrices like A and B and you want to check whether they are equal or not, the first thing you have to observe is about their orders. So you can compare two matrices, you can check for the equality if their order is equal. If the orders are not equal, then you need not even check for the next level. You need not even go to the next level. You can simply say, since the orders are not equal, the matrices are not equal. So now suppose I have one more matrix C, which is 1, 3 and 2, 4. So here also the order is 2. So the first case we concluded that A is not equal to B as the orders are not equal. Second case, here again A, I will say, is not equal to C, even though they have the same order and the elements are also the same. See, the elements are same, 1, 2, 3, 4. Here also I have 1, 2, 3, 4, but in different locations. That means the corresponding elements are not equal. See, here we have to check for the corresponding elements. If the corresponding elements are equal, then you can say the matrices are equal. Else the matrices are not equal. Here the first element is 1, here also the first element is 1. In both A and B, the first elements are 1 and 1, so you can say they are equal. But in the second element, A and C, they are different, because A's second element is 2, like A1, 2 is 2 there, and here A1, 2 is 3. Then these two matrices are not equal. So when will two matrices be equal? If I have a matrix D which is 1, 2, 3, 4 again, then I can say the two matrices are equal. So what is the use of this? Say suppose you come across a situation where A is given as 1, 7, 3, 5 and B is a matrix given as X, 7, Y and say some A, and he asks us to find the value of X. Say suppose, then and he says that A and B are equal matrices, then you can compare the corresponding elements to find the values of the unknown. So simply you can say X is equal to 1 and Y is equal to 3 and A is equal to 5. This is why, like when we need to compare matrices, when you need to find the values of some unknowns, then you need to compare the matrices. There you will compare the corresponding elements. You compare the corresponding elements to check for the equality of matrices. Next, let us see how we can add matrices. So suppose I have a matrix A is equal to 3, 7, 2, 5, right? And one more matrix I have B is equal to 11, 3, 5, 2. Here the order of the matrix, see when what are we trying to do here is I'm trying to find sum of A and B. You all know how to do it, but the precautions we have to take before adding is like you have to check whether the orders are same or not. If the orders are same, then only you can add, else you cannot, because you add the corresponding elements. If there are the orders are not equal, you don't have a option to add the elements. Say suppose I want to add A and D. Say so D is a matrix like 3, 1, 2, 1, 3, 4. I can add 3 to 3, 7 to 7, but I cannot add this 2 to anything here, and I cannot add this 4 to anything here. So that addition is not possible in this place, right? So when it is possible, when the orders are equal. If the orders are equal, that is the rows and columns are equal, then you can add. How do you add? Simply add the corresponding elements. 3 plus 11 is 14 and 7 plus 3 is 10. And 5 plus 2 is 7 and 2 plus 5 is 7. So we just add the corresponding elements to get the sum. Now let us find quickly B plus A. Suppose if I want to find B plus A, what is B plus A? So B plus A is 11 plus 3, which is again 14, 3 plus 7 is 10, 5 plus 2 is again 7, 2 plus 5 is 7. So I can say A plus B is same as B plus A. So we can say that addition is commutative. Addition of matrices is commutative, right? Now I have a matrix, say A is equal to 3, 7, 2, 5 is a matrix which I have, and I want to know the negative of this matrix. What is negative of a matrix? Is nothing but what is the additive inverse of the matrix, you can also say. So I want to find minus A. So how do I do it? It's nothing but a scalar multiplication of a matrix. Say suppose I'll multiply this with minus 1, 3, 7, 2, 5. This is nothing but the scalar multiplication of the matrix. That is, I'm multiplying the every element of the matrix with minus 1, which is minus 1 into 3 is minus 3, minus 7, minus 2 and minus 5. This is a negative of a matrix. In the same time, if I want to find a scalar multiple of a matrix, say suppose I want to multiply a matrix A, the same matrix, say 3, 7, 2, 5. I want to find, say 5A. I want to find 5A. So I'm multiplying it every element with 5. So when I multiply, 5 times 3 is 15, 35, 10 and 25. This is the scalar multiple of a matrix. Scalar multiple is nothing but you take a real number and you multiply each and every element of the matrix with that particular number, right? Now in the addition of matrices, say suppose I have three matrices A, B and C. Addition of matrices is associative, which is nothing but if I am adding A plus B plus C, it will be same as A plus B plus C. In other words, the order does not matter, like which two matrices you add and then you add the third one to the sum. It doesn't matter, like the sum of all the three matrices will come to the same always, right? So addition of matrices is always associative, right? Now let us talk about multiplication of a matrix. Suppose I have a matrix A as 1, 2, 3, 4 and say B as 2, 3, 1, 5. So how do we do this multiplication of matrices? See, multiplication of matrices, before going with multiplication, you should first look into the order of the matrices. See, it is always like whatever operation you do, you have to pay attention to the order of the matrix. See, when is this multiplication? See, multiplication is not possible always, like in the addition, like the addition of matrices is only possible when the orders are exactly equal. But in case of multiplication, the multiplication is only possible if the columns of the first matrix, is equal to the rows of the second matrix. Then only your multiplication is possible. Else it is not possible. For example, if I have a matrix A as m by n and I have a matrix B as say some n by r. Now here the number of columns is n here and the number of rows here are n. So the multiplication is possible here, right? And the order of the multiplied matrix, like the order of the product, whatever you get, the order of the product will be equal to m by r. It will have m columns and n rows when you are multiplying, right? So let us see how we do that. Let us take a matrix A is equal to, let us first do a simple one, 1, 2, 3, 4, and B is equal to say like 2, 1, 3, 2. Now let us multiply A times B. So how do we multiply this? We multiply the row with the column, right? The first element of the product matrix will be nothing but the first element of A times the first element of B plus the first row second element of A times the first row second row first element of the B. That is 1 times 2 plus 2 times 3. Similarly, in the second column also it happens, like 1 times 1 plus 2 times 2. This one into this and this one into this. Next, 3 times 2 plus 4 times 3. Similarly, 3 times 1 plus 4 times 2. And you get a 2 by 2 matrix, right? Now let us take one more example. You can calculate this, right? So let us take one more simple example. A is equal to say 1, 2, 3, 4. Now we'll take B with a different. So this is a 2 by 2 matrix. What are the number of columns here? 2. So let us take number of rows as 2, like 3 and 4. So this is a matrix of order 2 by 1. So what should be our product? Since this and these are equal, our product A multiple B should be of order 2 by 1, right? So let us see this, like 1, 2, 3, 4 multiplied by 3, 4. This will give us 1 times 3 is 3 plus 2 times 4 is 8, right? Now there is no row, no other column in the B matrix to go into the second column, so I am getting into the second row of the first matrix, so I should come into the second row of the product matrix. So it will be 3 times 3 is 9 plus 4 times 4 is 16. So we got a matrix of order 2 by 1. So this is how we multiply matrices. So whenever you want to multiply the matrix, like, you have to check whether the number of columns of the first matrix is equal to the number of rows of the second matrix or not, right? Now let us talk about the properties of this multiplication. You can clearly find when you do A multiplied B is not always equal to B multiplied by A. This is not always possible. A multiplied B, it's not commutative. Maybe in some cases it may be possible, like, you know, when you multiply with a 0 matrix, you get 0 always, or when you multiply with identity matrix, you know, A times 0 matrix is equal to 0, which is equal to 0 times A matrix. This is a case, and there might be some very rare cases where you get A cross B is equal to B cross A, but not always. Similarly, A multiplied by identity matrix is equal to A is equal to identity matrix times A. You know what is an identity matrix, right? 1 0 0 1. This is the identity matrix of order 2 by 2. 1 0 0 0 1 0 0 0 1 is an identity matrix of order 3 by 3. What is this identity matrix? Like, you have 1 in natural numbers, which gives us the same number when you multiply with anything, right? In the same way, identity matrix is a matrix which gives us, you know, the same matrix when you multiply with anything. Like, A times I is equal to A is equal to I times A. These two values will be always equal to A. It's like you haven't multiplied with anything, right? You are multiplying a matrix with 1, right? So this is not commutative. Multiplication is not commutative. Then when you have a multiplication, this is distributive over addition. You can say A times B plus A times C. So A multiplied with the sum of B and C is same as A multiplied by B plus A multiplied by C, given that the product is defined. What do you mean by the product is defined? It is that the orders are in our required manner. That is, the number of columns of the first matrix A is equal to the number of rows in the sum of these two matrices. In the same way, the number of columns in A should be equal to the number of rows in B. The number of columns in A should be equal to the number of rows in C. Then only this product is defined. And you also can say that product is associative. No matter what you multiply first, like, you multiply first B and C and then multiply with A, but don't write it on the other side. Like, it's not commutative. We have clearly mentioned that it's not commutative. So A times B C, when the order is not changed, like A B times C, these two are equal, right? Given that the multiplication is possible. If the multiplication is possible, then only you can say that the matrices are associative. The product is associative. Also, when you have two matrices A and B, say the product is 0, then A or B need not be zeros. Like, they can be, both of them can be non-zero matrices also. Generally in real numbers, or we have the product of two numbers 0, then at least one of the numbers has 0. But here they need not be zeros. Like, say, consider a matrix A is equal to, say, 0 5 0 0, and take one more matrix 7 0 0 0. And if you multiply AB, 0 times 7 is 0 and 5 times 0 is 0. 0 times 0 is 0 plus 5 times 0 is 0. 0 times 7 is 0 and 0. 0 and 0, you get a 0 matrix. But A is non-zero and B is also non-zero. These are two non-zero matrices. So two non-zero matrices product can also be equal to a 0 matrix, right? And if you take a unitary identity matrix, say A is equal to 1 2 3 4. Let us do with a simple one, like a 2 by 2 matrix, and the unit identity matrix is 1 0 0 1 for a 2 by 2, right? Now I want to find A times I. I told you, right, already, that when you multiply A and I, you get the same matrix A. Let us just verify it and then we'll move on to some problems. 1 2 3 4. multiplied by 1 0 0 1, you get 1 times 1 is 1 and 2 times 0 is 0. 1 times 0 is 0 plus 2 times 1 is 2 times 1 is 2, and 3 times 0, so 3 times 1 is 3, plus 4 times 0 is 0, and 3 times 0 is 0, plus 4 times 1 is 4. So where you get 1, 2, 3 and 4, which is nothing but our A again. So A times I is equal to A. Similarly, if you do I times A, you can verify yourself, it will be equal to A again, right? Now let us quickly solve some problems on these concepts now. See, the product of the two matrices is given as an identity matrix. So this is a 3 by 3 matrix, right? This is a 3 by 3 matrix. This is also a 3 by 3 matrix, if you can see. So your identity matrix also should be equal to 3 by 3, right? It should be 1 0 1, I'm sorry, 0 and 0 1 0 0 0 1. Right now, when the product is equal to an identity matrix, he is asking us to find the value of lambda. What will be the value of the lambda is what he is saying. So when you have the product, this is multiplication, right? Like when you multiply, it should be equal to this. So when we are comparing two matrices, we already learned that you have to compare the elements. So I pick the first element in the product. I'll take the first element of this product and equate it to 1. Then I can find the value of lambda easily, right? So what would be the first element? The sum, like, you know, the multiplication of the first row with the first column, right? Like, so 2 times minus lambda plus 0 times 0 plus 7 times lambda. The first one into the first, the second into the second element in the column, and the third in the row into third element in the column. This value should be equal to the corresponding element, which is equal to 1. So minus 2 lambda plus 7 lambda is equal to 1. So you get lambda is equal to 1 by 5 as the answer. So this is how you see. I told you, right, like when do we need comparing matrices? When the elements are exactly equal, why do we compare? Yeah, in this case, see, we don't know the value of lambda. So now we are able to find out the value of lambda when we compare the elements, the corresponding elements. And the second question is the product of these two matrices is given. A is a matrix which we don't know, and we have to find that value. And this is the product matrix given. Now, we already know, right, like when we are multiplying matrices, we should know the orders of the matrices should be same, right? Like, what is the order of this matrix? Let us write the orders first. Like, the order of this matrix is 3 by 1, and this is 3 by 3. Now, what should be the order of our matrix A? Tell me. Order of the matrix. See here, if I have to multiply this with this, the number of columns of the first matrix must be equal to the number of columns of the matrix A. So here, sorry, the number of rows of the matrix A. So here the order of the matrix A should be, the rows should be 1. What should be the number of columns? See, here we have seen that the product is equal to, we already saw, right, the product is always equal to the rows of the first matrix and the columns of the second matrix. So here the order should be 1 by 3. So here the matrix A should be of 3 columns and 1 row, P, Q and R, right? So now if I multiply 4, 1, 3 with P, Q and R, I get the product as 4P. Next, see, I have 1 row and 1 column, so there is nothing to come down, or there is nothing to go that side, right? Next it is 4Q and 4R, right? Similarly, 1P, 1Q, 1R, right? And then 3P, 3Q and 3R. So the value of P, Q, R will be equal to, you have to compare this with our given matrix, product matrix 1, 8, 4, -1 2 1 -3 6 3, and you get the values of P as -1, Q as 2, and R as 1. Right? So this is how you find out. So you should figure out like what should be the order of the matrix. If you don't figure this order of the matrix out, you are never going to get this question. Right? And the next question is A alpha, the suffix alpha. Here the alpha, suggests about the angle given here. A alpha is given as cos alpha, sin alpha, minus sin alpha, cos alpha. We have to find A alpha times A beta. So first let us write what is A beta here, which is cos beta, sin beta, minus sin alpha, sin beta, and cos beta. Right? This is A beta. Now I'm trying to find A alpha into A beta, which is cos alpha sin alpha minus sin alpha cos alpha times cos beta sin beta minus sin beta and cos beta. So the product is cos alpha cos beta minus sin alpha sin beta, and then cos alpha sin beta plus sin alpha cos beta. Similarly, minus sin alpha cos beta minus cos alpha sin beta, and here minus sin alpha sin beta plus cos alpha cos beta. So this is in the form of cos alpha plus beta, and this one is in the form of sin alpha plus beta. This, if you take the minus sign common, it is again sin alpha plus beta, because when you take minus common it becomes sin alpha cos beta plus cos alpha sin beta, which is again sin alpha plus beta. And then this one is also in the form of cos alpha plus beta. So this is nothing but A alpha plus beta. So we can say that A alpha A beta is equal to A of alpha plus beta. This is how you solve this question. And finally, if the diagonal of a matrix, say suppose I have a matrix A which is say 2 0 0 2. It's a diagonal matrix, right? The diagonal here is 2. So what will be A square? 2 0 0 2. I multiply it with 2 0 0 2, right? So what do I get? 4 plus 0 is 4, and 0 plus 0 is 0, and 0 and 4, right? Similarly, if I do A cube, I get 8 0 0 8. So when I have a matrix of any matrix, any order, and the diagonal here is, what is the diagonal here? 2 comma 2. So if I have a matrix A B C, and say I have elements A1 here and A2 here, A3 here, and so on for a diagonal matrix, then the A power n, see this is, if you look at this, this is 2 cube, this one is 2 power 4. So if I do A power n, it will be 2 power n, right? So when a diagonal elements of it, see we are just writing the elements of the diagonal, like D1, D2, D3 and so on are the diagonal elements of a matrix A. Then the elements in A power n, the diagonal A power n, they will be D1 power n, D2 power n, D3 power n and so on, Dn power n. So you just raise the elements of the diagonal to the same power where A has, right? I hope you understood these things. I'm sure that you already know all these concepts, but I just wanted to revise these topics. And let me see if you have any questions, then we'll discuss on those questions. Yeah, I hope you understood this topic properly, because I didn't get any questions from you guys. So we'll meet with another interesting topic on matrices in our next session. Till then, signing off, Satish from Toppr.